Hello, and welcome to the video for section 6.1, exponential growth and decay. So we're going to start off and talk about an exponential function. An exponential function has the form y equals a times b to the x, all right, where a cannot equal 0 and b is a positive real number other than 1. All right, it's called exponential form because we have a variable as the exponent. All right, so we're going to start by talking about a growth function and a decay function. So first off, if our a is greater than 0 and our b is greater than 1, then our equation a times b to the x is an exponential growth function. All right, and b is called the growth factor, all right, how much it's growing by. All right, so as we go through and look at, there's a kind of a graph here, and it tells us all kind of the similar stuff. All right, the important part about this graph, it has some key points that we can look at, but it's also this word that we call an asymptote, okay? What an asymptote is the line will approach the graph more and more closely, but it will never actually get to that value, all right? When we talk about an asymptote, it will approach that value to our extremos, okay? So either our positive infinity or our negative infinity, all right? So it's gonna get closer and closer, but never really touch, all right? So that's what an asymptote. In our graph here, the x-axis is an asymptote of this, all right? So when we go and talk about the domain and range, the domain of this function is negative infinity to infinity, and the range is 0 to infinity. Notice we use a parenthesis here because it will never actually get to 0. Okay, it will get really close to it, but never get there. All right, so that's exponential growth. The next example we have here is exponential decay. So this is our parent function of exponential decay down below here. All right, and what it's going to show us here is if a is greater than 0, and b is greater than 0 but less than 1, then our a times b to the x is an exponential decay function. And b is called the decay factor. All right, that just kind of goes in line with if we take a number greater than 1 and raise it to a positive exponent, the number will get bigger. If we take a number between 0 and 1 and raise it to an exponent, right, that number will get smaller and smaller. So notice here in our graph, it's exponential decay. The bigger the x number is, the smaller our y value or f of x value would be. All right. Notice our x-axis is still an asymptote of the graph. So our domain is still all real numbers, and our range is still the same. Okay. So that's some basis of our exponential growth and decay functions. All right. So this has a lot of real-world examples. All right. And when we talk about it, it says some real-life quantities increase or decrease by a fixed percent each year or some other time period. All right. The amount y of such a quantity after t years can be modeled by one of these two functions. The way we'd set these up, an exponential growth function or an exponential growth model would be our initial amount, a, times 1 plus our growth rate, all to the t, okay? A is the initial amount, all right? Our r is the rate, and this is important, as a decimal, and t is time. All right, so that would be an exponential growth model. So whatever our growth rate is, it's going to be obviously this number inside the parentheses is going to be bigger than 1. An exponential decay model looks very similar, but there's only one difference. Sorry for the math pun. It's subtraction. A is the initial amount. R is the rate as a decimal. and t is the time. All right. So as we go through this, each of these questions is going to access something a little bit different. All right. So our first example here says the value of a car, Y, in thousands of dollars, all right, can be approximated by the function Y equals, all right, 25 times 0.85 to the t, where t is the number of years since the car was new. All right, so if we go through here, we're going to tell whether the model represents exponential growth or decay. We're going to look at this number inside the parenthesis. If it is less than 1, this is going to be exponential decay. All right. Part B is now going to say, identify the annual percent increase or decrease in the value of the car. Well, if we think of this 0.85, we know it's decay, so we look at our decay formula up here, and this would tell us 1 minus r equals 0.85. All right. So if we subtracted 1 from each side, and then divided by -1, we would get r equals 0.15. But remember, this decimal, right, we want to know what the percent increase or decrease. So if we made this a percent, we would say that this is 15% decrease. All right. Please be careful when you go through and do this. What happens a lot of times is kids just take this number here as a percent decrease. All right. Well, it's a big difference, 15% decrease and 85% decrease. Okay. All right. So our last one here says estimate the value of the car. All right. Or estimate the value of the car will be in year 7. Estimate. Oh, it should be what? Sorry. All right. So in that case, all we're going to say is that t equals 7. So we're going to take our equation and just plug in 7. All right. And I'll just show you on the calculator here, right? We would do 25 parenthesis 0.85 and raise it to the 7th, right? And we would get y equals 8.014427207 ... All right. But we're talking about value here, so we're talking about money. We need to go back. Remember, this is in thousands of dollars. So this would be $8,014.43 after 7 years. Okay? So we don't want to just say 8.014, right? They want to ask the value. We need to actually figure out what the value of the car is. All right, let's take a look at example 2. All right, another great example of exponential growth and decay is population. In 2000, the population of a city was about 1.04 million. During the next 14 years, the population increased by about 2.05%. So now they're going to ask us to write an equation of this first. All right. So when we estimate this, we have to write our model. So we would say that our initial amount is 1.04. That's millions of people. Our rate is 2.05%. So as a decimal, we'd move the decimal place over 2. That would be 0.0205. All right, and now we have enough information to write our equation. All right, so we would say y equals 1.04 times 1 plus our rate as a decimal, all to the t. All right, so to simplify that, we would just say 1.04 times 1.0205, all to the t. Okay? Now the last part here says there are going to be 2 similar questions. Estimate the population in 2008. Well, in 2008, that would tell us that our t is 8. All right, if we did that, that would be roughly, approximately 1.22, or we would get 1.2233124995, right? But we're talking about millions of people. So this would be 1,223,312 people, all right, in 2008. All right, so we have our two things here. We have our equation for the problem and our population in 2008. All right, we would really put the decimal place all the way over here because it's millions. So we'd move it over 6 places. And remember, we can't have part of a person. So that's why we don't have that. All right. The next question on your notes will be fixed, but it says estimate the population of, or when the city, or estimate the population in 2010. So in this case, we would just say that T is 10. And if T is 10, we would say 1.04 times 1.0205 to the 10, and we would get 1.273982405. Okay, so if we did that, the population in year 2010 would be 1,273,982 people. All right, once again, we don't want to round to partial people. All right, so these have some limitations where we can only have a certain time frame, but they said during the next 14 years, they'd all be realistic values. All right, populations won't continue to grow at the same rate over that longer periods of time, but for fixed intervals, it can be very helpful. All right, our next example talks about rewriting an exponential function. When we want to rewrite an exponential function, what we're going to do is they want to know, all right, the amount in grams of radioactive isotope barium-140 remaining after T days is given by this equation, where A is the initial amount in grams. What we really want to know is what percent of this decays, all right, each day. We don't care about the initial amount here. What we're going to do is we're going to use our properties of exponents to rewrite this as 0.5 to the 1/13th. All right, and I'll do this off to the side here. But if I did T times 1/13, that would give me T over 13. So I'm just rewriting this using those properties in the back of our Chapter 5 cheat sheet to go through here. So what I would need to do to go through to get this value is I'd have to do 0.5 to the 1/13th. And notice here, I would get 0.948, let's round to 4 decimal places, 1, all to the T. So now we can see here, it's very similar to our exponential function model, that this number is less than 1, so it's decay. But they want to know what percent decays each day. We would go through and do 1 minus our R, and we'd go through and get our R to be 0.0519. But they want it as a percent, so it would be 5.19% each day. Okay? Please make sure you understand how to manipulate these exponents. There'll be questions like that on your homework and on future assessments. So make sure we understand how to do that. Okay. All right, on to the last thing for today. All right, something you guys all care about, money. All right, invest money when you can early. It pays off in the long run. So compound interest is interest paid on initial investment, called the principal. All right, and on previously earned interest. Interest earned is often expressed as an annual percent, but the interest is normally compounded more than once per year. Consider that the principal, P, deposited in an account that pays interest of an annual rate of R as a decimal, compounded n times per year, all right, where A is the initial amount. All right, so just to make sure you realize, P is the principal, All right, R is the rate as a decimal. N is the number of times compounded. And T is the time. All right, when we talk about times compounded, quarterly would be 4, monthly would be 12, yearly would be 1, daily would be 365, okay? So, for example 4, it's gonna tell us that we deposit $8,600, so that's our principal, at 1.32%. All right, so we need to turn that into a decimal. So 0.0132. All right. The balance after T equals 4 and N equals 4 because it's quarterly. So our N would be 4, our T would be 4. All right. So this is where orders of operation is going to be important. All right. We plug everything in here. All right, if you want to simplify the exponents, you could, that'd be 16. All right, what I like to do as I go through this, I like to do the division first, okay? And please understand that you can type this all in one step. It's just easier to make sure we can save errors, and we're going to keep everything in our calculator. The division first, then I do still what's inside the parenthesis, plus 1. Now I'm going to do exponents, so I'm going to raise it to the 16th, which is 4 times 4. And times 8,600. So after 4 years of this money being invested, compounded quarterly, right, we would have $9,065.49, okay? Please make sure you think about these things realistically. If you were to do one of these steps wrong and you got like millions of dollars after only 4 years, that's not very realistic. As much as we'd like it to have happened, it's just not realistic, okay? All right, the second part of this example is find the balance after 3 years when the interest is compounded daily. All right, so our principal is still $8,600. Our rate is still 1.32%, which is 0.0132. All right, our N now is 365, and our T now is 3. All right, so we plug in our formula. 1 plus 0.0132 over 365 to the 365 times 4. All right, same steps, the division first, divided by 365. Don't worry about that, plus 1. We want to raise that to the 365 times 4, and then multiply our 8,600. So we would have $9,066.27. Okay, so we can see what happens here. It's kind of showing us something that the more often that the interest is compounded, the more money we're going to make. So notice here, it's a year less, but because our interest is compounded more often, we end up with more money. Okay, so that's the video for 6.1. Your homework will be posted shortly. All right. Oh, my bad. Never mind. It shouldn't be to the 4. It should be to the 3. Sorry, let me fix that real quick. All right, that's my bad. All right, so that should be to the 3rd power. All right, so if I go through and do this again, all right, we do 0.0132 divided by 365 plus 1. All right, whoop, there it is. So that should be $8,947.39. Okay, sorry about that mistake, ladies and gentlemen. All right, so that's a video for 6.1. Your homework will be posted shortly. If you have any questions, please let us know. Have a great day.